folks, before we dig into today's episode, pun fully intended, make sure you hit that subscribe button. If you geek out over ground movement, slope stability, or just want to hear wild stories from beneath the surface, this channel is built on a bedrock you can trust. We break down the infrastructure beneath your feet, one project at a time. Today, we've got a real field warrior with us, Louis Schulte, a senior geotechnical engineer who's worked everywhere from chaotic oil field to high-stakes bridge foundations. If you've ever wondered what it really takes to keep a highway from sliding off a hillside, you're in the right place. Louis, welcome to the show.
Pleasure to be here, Michael.
Excellent. I was wondering if you could just give us a quick introduction to yourself and a bit of your history.
Like I said, my name is Louis Schulte. I am a senior geotechnical engineer at E.L. Robinson Engineering. I work out of our Columbus, Ohio office over here in the States, and I've been doing this about 14 years now. And so I specialize in everything from highway embankment design to bridge foundation design to landslide repair and a number of little commercial projects in between.
Excellent. So just so the kind of audience knows, we met the other day in Albany, in Columbus. I just wondering if you could give us a bit of a background. So you mentioned about kind of you started work on a farm environment and then, some early field experience. I wonder if you could just tell us about that.
Of course. So background is I grew up on a farm here in Ohio. So I've lived here my entire life, went to school. Farming background was a great start into the engineering world. We obviously are working on large scale field size projects. And the handy part is that we're using some old fashioned survey equipment to lay out stuff. So that's definitely where my engineering interest came from. And then as things moved on, I went to school in the University of Dayton, also in Ohio. And while I was there, I worked several semesters and internships as a drill rig helper. And so I worked for a company that did soil sampling, and it was an absolutely amazing background to work with people who are sampling soil, testing soil, running in situ testing, as well as laboratory testing and everything like that. So I can't speak highly enough to the internship experiences that I had. And specifically, you're definitely getting that hands-on experience to the background of all of our engineering mechanics by all the laboratory testing, all the in situ testing that we do out in the field, as well as just we also did construction material testing and the ability to rub things in between your fingers and feel the physical world that we work in.
Sure, excellent. So in relation to the farm, so you're obviously used to hard work, long hours, which can help, in our industry sometimes when you're out on the field, having some really good field experience helps you from, transitioning from being in the field all the time to actually going into the office at some point. And you can actually answer questions with, actual validity, I suppose, because you've been there, you've done that. You haven't just gone straight from college straight into, the workplace, being in the office. So in terms of what you're saying about the lab tech, you kind of covered that a little bit there. What kind of lessons did you learn from being a drill rig helper and a lab tech? I wonder if you can just expand on that a little bit more.
One of the funnier parts, one of the worst lessons you can learn is as a field hand is how to speak like they do. I learned some very foul language and very crude jokes, but specifically, you end up having this goofy complementary skill set. I worked around some really, really roughneck characters out on the drill rig, and they were just pleased as could be to have some, a detailed little engineering helper who did nothing but take notes all day. And so I was happy if I was taking notes and holding a clipboard, it meant I didn't have to go with the rest of the rig helpers to go haul augers around or to, sample. So logging samples ends up being kind of a nice little niche into the world.
Struggling to find top geotechnical and geoenvironmental talent? You could use a generalist recruiter, or you could use a specialist. At Geo Expert Search, we place experts where they belong. Across the UK, USA, Australia, and New Zealand. No highways, no bridges, no structures. Just geotechnical and geoenvironmental. Now and forever. Geo Expert Search. Finding the right people for the right roles with no wasted time. Visit geoexpertsearch.com to learn more.
And Yeah, every other lesson is just a lesson of the physical world, right? In our university laboratory testing, our university classes, we might run one Atterberg limit, and we might run one Proctor sample, and these things as sort of an example day that we do once in a semester, and suddenly now you're responsible for getting 20 of these tests done in a day for months on end. So the lessons are just a great repetition of how all these tests are run.
In terms of, I suppose, the initial kind of fieldwork aspect as well, and the kind of starter jobs, would you say that teaches you more? Because obviously we'll all go and do the geology degree, or maybe a civil engineering geotechnical degree. So you kind of have the academics, but then once you're actually sort of thrust out onto site, then it can be very different.
Well, yeah, absolutely. But what this maybe a side note to your question, but one of the biggest lessons you learn is just how to be around large equipment. And all of a sudden, as an engineer, this is like my biggest fear is that, we go out into the real world, and every time I bring somebody with me, I can't let them leave my side because so many of our young engineers struggle with just being in the presence of these large scale projects, and how do you move safely about? And going all the way back to my farm background, that's something obviously you can carry with you for decades now, and just a tremendous help.
When I was working on a sort of piling project in London. I think it's Google headquarters down there, and they have very contaminated land. So they have to put in piles, test all the contaminated land, remove it all around. But there's lots of things going on around us. It was quite a small environment, and you really have to have your wits about you, just because of the machinery back and forth constantly. Otherwise, you get clipped by one of them. I seen there's someone ran over by one of the large mining trucks, and they're so huge, like a normal truck is kind of you can't even see. So yeah, health and safety in our world and all worlds, I suppose, is extremely important, and you need to adhere to all the protocols.
Yeah, of course, and like I've attended so many we call them toolbox talks, but I've attended so many toolbox talks and safety meetings just because they will refuse to let these engineers come on site and just kind of wander about willy nilly now. It's an experience that keeps paying off years later.
Yeah, it definitely does. That's what we do here in the UK. Well, I mean, the US at the moment, but toolbox talks on a daily basis. Start of the sites, maybe something that can be improved, something that may have happened, whether it's weather change, anything like that that can just keep it sort of front of mind for to move forward, have a safe site. So I was wondering if you could tell us a little bit about Ohio's design and build model, kind of high pressure and environment in which that creates.
Sure. I'll give my full disclosure. I work in Ohio and West Virginia, so I can't speak to like how well everybody else does this, but I do. I have traveled nationally enough to know that not everybody handles these design build projects, but uh, Ohio, I think, does an excellent job of trying to push the envelope in terms of innovation, or of however we want to define that, of project scheduling and getting it to move faster and design faster. So, at least in the Ohio model, designers team up with contractors. We form a marriage, for lack of better terminology, and we move forward on a project together. And so, it it allows us to sit down with a contractor and really harness in on what are your pinch points on this project. What do you think is going to be your major scheduling problem? What is the and then in Ohio specifically, we Ohio allows you these excellent opportunities to kind of sharpen your pencil, and a contractor will say, "Hey, what if we tried this? We think it'd be easier to build it in this way." And I'll be the first to say I think our engineers are, I don't want to say stuck in our ways, but we have our habits and our ways that we do things because we've always done them. And so our contractors do an excellent job of saying, "Hey, we think we could do it a little bit faster, but we need this," or "We think that this construction technique might be a little bit cheaper." And Ohio allows us to capture these big wins, and when we move forward on this project, and yeah, it's an increased risk on our end, But if you're married to this good contractor, it benefits everybody, and it allows us to sharpen our pencils. It allows us to bill out at higher fees, which is always nice. But I think most importantly, allows us to move forward on projects in such an expedited manner because we're married to this contractor. They we can start designing with them in mind. They can give us almost immediate feedback, and then as we're working through a project, they put us right on the phone. We drive out to the site. We handle. All right, we ran into X problem, and now it's all right. We're not leaving until this is solved. And so I don't want to say it cuts the Ohio Department of Transportation out, but it allows the contractor and engineer to work in a much closer fashion and solve problems as they sort of show up rather than relying on the state to be the go-between.
Sure. So I suppose in your experience, you would have done that a few times. What was your kind of most effective call that basically, solved the problem, allowed it to continue, and not there being any delays and costs associated with that?
Well, I guess the first one that comes to mind, we were doing a landslide remediation that was beneath an existing retaining wall on the highway that supported by that retaining wall, and we had loads of boring coverage down in the slope, and we also had geophysical testing, so electroresistivity testing, and our primary concern was the top of rock elevation fluctuated in ways, and so we were installing drilled shafts along the slope to try to stabilize it, and of course, as almost as these things always go, the top of rock elevation, despite all of our testing and despite all of our borings, the top of rock elevation is not where we think it is. And in some places, it's just a little bit lower, and in some places, it's a lot lower. There's these weird valleys we never captured, and the design build process, rather than in a traditional design bid build, this would have been a major change order and a major problem, probably requiring months of back and forth between contractor and state agencies and stuff. Uh, Instead, it turns into a phone call to the engineer, and we go, "Oh boy!" And so we immediately took the steel beams that we had for reinforcement in those drilled shafts. We obviously couldn't get them resized, but we could stick cover plates on them, and it was just a little thing that no one else really knows on the project, but we can sort of go, all right, we are able to at least tie in a scab in a solution that otherwise would have taken months of delays and change orders and costs to rehabilitate. So that design build process permits that the direct line of communication, and the social pressure forces us to get this thing figured out quickly.
That's it. When you have the pressure, sometimes you can do amazing things and get stuff done much quicker. So at the start, we kind of introduced yourself as having some experience on or sort of working on oil field projects. I was wondering if you could just tell us a little bit about the unregulated chaos of shale plays whilst doing that.
Yeah, I'll hide all the names of those involved for their own. But I think we're out of the statute of limitations. So, the timeline here is Ohio's shale play picked up in about 2015, and until about 2016 or so, the it was. I don't want to say it was unregulated, but even the regulators were overwhelmed with their ability to sort of monitor how these well pads were constructed. And for your audience's reference, we're sort of in the hilly areas of Ohio, the unglaciated part, and the major problem is we have really weak soils and like unusual shear plane orientations, and very layers of just extremely weak clays that are trapped in between other layers of much stronger clays. So the problem that we ran into was just I mean, this is my personal opinion. We had contractors come up from like the state of Texas. These drilling contractors came up, and I certainly can't say anything bad about them, but they came up and they had no practical experience working in these geological conditions. And so they come up and they hired whoever they could find, or maybe they brought their engineers with them. And so they just started chopping off the tops of hillsides and sort of spreading them out and filling them. And they had no idea about any of the local building practices that are used to dealing with these weak soils. And next thing you know, we had pad failure after pad failure after pad failure. And finally, that's when we got called in, and they were like, "We need to get some local expertise. Like this has gone on far enough. We've had 7 or 8 of these things fail now. We need to get some local experts." And that's where we come in. And it is, if you're like us and you're used to dealing with highway administrations who work on that years and months long timeline, contractor or the oil fields around here especially would say, "All right, well, our drill rig's coming in 6 weeks, so you can go ahead and get us that ready. It costs us $200,000 a day every day that rig sits. So, here you go." And immediately it's like, "All right, well, we'll sketch something up on a napkin. We'll start our design process." But in the meantime, I was sort of, they sort of task you and they say, "Hey, come into our office. We need somebody who can be both the engineering rep, the owner's rep, the construction inspector, the construction manager. We need to just go ahead and handle all that. We're not really our cup of tea." So you end up taking on this weird do everything role for them, as well as doing just our regular engineering design. And like I said, they say, "All right, well, the rig's coming in 6 weeks. The rig will be here, and we need this pad to be functional by then. And here's a blank check. Go ahead and figure out what it takes to get it built." And so that's kind of our background in there. But it doesn't change the geotechnical conditions, and it doesn't change the fact that the hillside's already failed. So we have to get back on this thing quick as possible.
You mentioned kind of having people local, whether that's the drillers or whether it's the engineers, the geologists, having experience in the local geology and that sort of thing can be very beneficial. But sometimes, from where we are in the UK, you maybe have some people from the south that will just win the tenders to go north and vice versa. So sometimes they're not quite, but the day rate or the amount overall seems to be cheaper. So then they select them, but then you can potentially, if you don't have an experienced enough driller, for instance, have some issues with certain geologies when drilling through, having to change flush methods, that sort of thing.
Isn't that how our field always works? Everybody knows somebody cheaper, but man, you can't. It it is never a good idea to go. Local knowledge is local knowledge, and that's something that you can't. Doesn't come cheap.
Definitely, definitely. So we were just going to kind of go on to the stuff that talks back essentially how instrumentation, so the top tools, AMTS, piezometers, and inclinometers. I wonder if you could tell us your experience and a bit of background about that.
Yeah, I had a really fortunate start to my career. There was a hydroelectric plant being installed on the Ohio River, down here in Ohio, West Virginia, on that border. And we had a maybe an 80 or 100-foot excavation, and we were tasked with sort of designing the excavation as well as the instrumentation plan for that excavation. And golly, we're talking some of the most sophisticated instruments in the world. And I am a 23-year-old engineer being told to go install these things with the owner's representative. And it turned out to be an enormously good experience and something I've take with me today. I still think it, we don't get, in our geotechnical world, we don't get the privilege of just ordering a piece from the factory. We don't order our steel. We don't order our concrete. We are stuck with whatever we have on site and how is it going to behave. And so I think our geotechnical instrumentation is crucial to making sure that the soil, that the mechanical properties that we assign are are accurate, but more importantly, like what are our stress strain relationships? How much is this thing allowed to move before we're concerned about it moving? And so that, we are installing these inclinometers as an example on these job sites to monitor these excavation or monitor these embankments. And same with the well pads that was telling you about. And same with the landslide repairs that we do on the highway side. Like, there's no truer way to verify your work than to install one singular inclinometer out there that says, "Hey, we've measured this thing. We measure this thing every 6 months for the last 10 years, and it has held up." And how could we do better than that as an engineering firm to provide our final expertise to show this has not moved at all.
Yeah, definitely. So could you give us an example of when instrumentation told the truth that drawings have potentially missed?
Yeah, so that's a good question. The drawings missed. I mean, ultimately, it does go back to what we talked about. Like, we've worked on projects where we install piezometers and we find out we have artisanal well conditions, and this is still something I try to wrap my head around. We've gone on, for example, these well pad projects. We would You'd be standing on the top of a hillside and you could see for a mile in any direction that you're at the highest elevation, and we had a pad failure on one of the side slopes, and here there's water coming out of the ground, and you're going, I don't know much about water. In engineering school, all they taught me was that it flows downhill, not uphill. And so here we are. If we have piezometers on each of these embankments, like we can find these things, and that's just a classic case. So now that's when we really started our big push to get our well pad designers. Hey, can we install just one inclinometer on this failed slope? And we can come back. We can come back every day for 2 weeks. We can come back once every 2 months. We can come back every 2 years. You guys need to, if you're going to put this $20 million rig on here, well, one little teeny pipe in the ground that goes down vertically will tell us the story of whether or not this thing can safely be here. And if you guys bring that same rig back in 2 years or 5 years to refract or redrill another well, all we have to do is, take one more reading, and then we can at least give ourselves a thumbs up. Hey, there's nothing going on. This is not slowly moving down the hill. We don't have this local slip plane that we've developed in one specific area that we just can't quite see yet. So the instrumentation is always something that you can't. It looks expensive on the front end, and it is expensive on the front end. But man, the back end, I don't think our audiences appreciate enough just how much you can get a seal of approval on something like that.
Excellent. I was wondering if you give us one monitoring win or fail that has stuck with you, or perhaps you'd learned something from.
Well, here's a fail I could give you. We're building an MSC wall, so mechanically stabilized earth walls. I'm not sure, maybe you have a different name for them in the UK, but right, we have these panels being constructed, and then we're filling on the inside with uh, the reinforced fill. And we put one small settlement platform in the middle of the slope because we thought we'd see maybe 24 inches of settlement. And so we install this thing and we get it, and they start burying it. And it had been installed for 3 days. And contractor calls us, hey, that little, our settlement platforms run out with a piezometer and a hydrostatic tube that run out to the readout box where you can read it. And of course, they were digging the foundations for the next layer or the next set of panels that would go in. It cut right through it. And like, what can you do then? These things take 8 weeks to get shipped back in. The contractor's obviously not going to wait on us that long to get it shot back in. We tried to get it repaired. It never worked right again. And it was just a classic example of you have to think with the idea that these contractors are not going to intentionally try to hit this. I would never say that about our contractors, but boy, they seem to find it more often than not.
Yeah, these things do happen, don't they? I was wondering if you can just tell us a little bit about the overcomplication that can happen in engineering and how to potentially avoid it.
Overcomplicated, like this is so I'm a fan of your shows here, and like one of the things that I think we tend to touch on as engineers, whether it's on podcasts or even at our trade shows, we always want to talk about the next technological wave that's coming, and how are these things going to shake up, or they're going to completely transform the industry. I tend to think it's the exact opposite. We tend to forget that there's a lot of these things that are going to remain the same for the next 50 years, the next 100 years. And it's like we're still going to use soil, we're still going to use concrete, we're still going to need steel. And so we talk about overcomplicating plans. Like we've done such a great job at generating new technologies to design, whether it's three-dimensional technologies or, high-powered computer programs to do finite element type things. And lo and behold, the difficulty we've always run into is we still need a simple way to explain this to the reviewer, to the owner, to the whoever that makes us comfortable with what we got. I think the complicated answer that we often calculate ends up costing us in the sense that none of us engineers has enough expertise to look under the hood and know how does this finite element program operate? How do these modeling programs operate? And I'll give you one example. I do a lot of work now mentoring our younger engineers, and they're always shocked to see. I wish I had one here. I pull out my three-sided engineering scale when they bring me over a plan set, and I measure off something. Well, that's wrong. And they go, "What do you mean?" And I pull out a three-sided engineering scale, and they go, well, I thought that was like a fancy straight line device for drawing straight lines. And so I say, well, if you were truly a contractor working on this job, how would you lay that? How would you build this? And there's a slow bit of thinking, and I go, we can't just expect to give every contractor we have nothing but digital files. Like a lot of times they need to be able to, the ideal plan set would carry something like the ability to measure off of that stop sign, or we can measure off of this pipe, go down this many feet. We should be able to come up with plan sets in our world that allow us to measure things into the physical world as they
And
exist.
practical application of it rather than a, you know, removed sort of 3D image potentially.
Yeah. Especially in some of these undeveloped parts of the world too, like the the where we can't afford to get, survey control and every last digital device in there to load in our shape files and things like that. Some of this just needs to be, oh, we need to bring this pad level down a few feet. We need to get water sloping over in that direction. We need to, cut this slope down. We don't have enough room to get that toe of embankment installed. All these little things that yes, there's a benefit, and there always going to be a benefit to the digital files, but a lot of times we forget, like, especially these are just things that you notice when you're training younger engineers, that we forget that the world that we live in today was constructed by people working outside the digital world. They had plan sets, and they learned how to read a plan set like this and then mirror it over that way for their bridge cross frames. And so they it was so much work for them to draw it out that they had to come up with simple plans. Otherwise, it would have just totally destroyed the entire thing. So, I think as engineers, we need to focus on that a little bit more.
Yes, it's a good point. In terms of, you mentioned mentoring people, what do you tell your kind of young mentors? What are sort of common things that you would advise them on?
The common things are always that, like, it's always some version of, hey, you're still young, so go out and learn something. And I love the company I work for, and we do hire interns, and I do my best to teach them. But I always caution them and pull them aside a little bit and say, hey, if you think this is something you might want to do, we'd be happy to have you back or whatever. But I think there's always great opportunity to go work for a contractor for a summer, or go work for a driller, or go work for some sort of laboratory testing firm, and go learn a bunch about something that you're not going to pick up here. So, I've mentioned all of my previous work background. I think one of the greatest things that I was able to pull with me was this sort of localized knowledge that you can't. We always preach about the need for local knowledge in the engineering world, but you get it from your drillers, these roughneck drillers that have all this experience drilling all over the state or all over the region. They're the ones who are carrying this knowledge with them, and that these are the people that we need to be speaking to. And rather than relying solely on your university professors, and once you come work for us, well, now we need you to know this stuff. But if you want to learn some of these things, I'll use an example. We've had master's students come in, and it's like they barely touched soil ever. They took their one laboratory class in university, and that was all that we did. And it's like, oh no, no, the greatest thing you could ever do was to go work for a laboratory for a summer, learn about the plasticity limits, and learn about how we measure field densities, and learn how do you make these judgment calls out in the field when we're you know when we're working. That a lot of times as engineers we run into the downside of, hey, let's stop work for the day, we'll go home and we'll make a decision and we'll work through this problem and stuff. And I think we forget that the rest of the world's still running. These people every one of these people is paid, and they need a decision now. They need a judgment now to determine, can we keep working? Is this safe? Does this product meet the engineering standard that was outlined in the plans? And so I'm a huge advocate for, you work for a contractor and they think only in the terms of like time and materials, and how do all these things come up, and does this plan set show a finished product that is constructible? In what order would you do these things? And so I always caution our interns that, like, I think it's great. I want you to come work, for the summer or for the semester or whatever. I want you to have a great experience. I want you to learn a lot. But I think there's so much outside the engineering world that we can't teach you once you are an engineer. So that the time to do it is when you're young, and you can grab this little bit of extra experience.
Yeah, definitely. Well, especially working in a lab is particularly good because you would be out on site, maybe it's conducting test pit or drilling sort of horizons from drillers. So, and you'll have maybe that kind of a logging sheet which will define everything as a kind of graduate, but it would help to work in a lab. I think people in the lab, certainly at the start, would have a much higher degree of knowledge in the thing that you're actually doing on site. You have lots of other things on site to do, including managing the driller and where you'll go and the health and safety aspects. So when you put in your results and then you get them back for a PhD or something, you find out, oh, actually, it was something slightly different to what I thought. So it's always a good thing to kind of go in and learn there. I was wondering if you could give us the kind of biggest myth that you think is around in geotech at the moment.
I this this was something we had just kind of discussed, but I think the biggest myth is that we're going to stumble on some great technological revolution that's going to change the world. And I think all the answers are right there in front of us. We talk about, well, is AI going to change the world? I don't know. Like, if you use AI to write your foundation reports right now, or like, what does that say about your ability to write? If you use these fancy digital models to kind of outline the entire design of how you're going to do something, oh gosh, we are constrained to the physical world that we live in, and we've already built a pretty nice one at that. And so the question should always be, it, does this technology allow us to see something that we couldn't do before? And if yes, then like, maybe we can keep it. But I read so many of these uh, you know PhD dissertations or master's theses, and a lot of it comes across as like we tried solving a problem that didn't exist. It's not always clear that we've been estimating material properties for decades now based on blow counts, and now all of a sudden we tried to invent a new way to estimate, and it's like, guys, I don't know, that seems like a problem that we've already solved.
Yeah, yeah.
Uh, maybe as now on the flip side to that, I have a little bit of background in PDA testing of driven piles, and that can be a hugely valuable resource, because you know, all we've ever known is that piles, when you hit them, they start to develop capacity as the farther down they go, and we kind of have some rough ideas based on how heavy the hammer is and how far it fell, and this is roughly what our capacity is. But I think that's where one area where we've said, "Oh wow, like we've found this little device. All we got to do is attach these two little things on there, these two little sensors, and it measures how they and we can get something close to a capacity in a lot more of a expedited manner." So I like right sizing the technology to the job is probably the biggest myth that I think we need to have conquered.
So, Louis Schulte, thanks for reminding us that great engineering, it doesn't always need something complex. It just needs to work. Folks, hit the subscribe button. If you've learned something new today, drop the site story in the comments, and don't forget to subscribe for more ground insights as like this. Louis, thanks very much for giving up some of your time and coming on and sharing some of your experience and stories with us.
My pleasure.